Hello everybody, my name's Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the 737 MAX differences. So in this presentation we'll be looking at the differences between the MAX and the NG series. Of course you have to understand this can't be a definitive list of all of the differences, but it certainly includes all of the significant ones. And we'll be covering the MAX family, Powerplant, landing gear, fuselage, APU, fire protection, air systems, a miscellaneous section into which I've thrown all kinds of odds and sods, wings, the fly-by-wire spoiler system, onboard maintenance system, and the MAX display system. As always with these presentations, please treat your company training and their manuals as the authoritative source of information. Okay, so let's take a look at the family of MAX aircraft. So far there are 7 versions. Starting numerically with the 7. Now this is just at the time of recording finished its certification flight testing, but isn't yet in revenue service. The next one up is the 8, which was the launch aircraft. And a sub-series of that is the 8200. Main difference there being the flat pressure bulkhead and a number of other cabin changes enabling 200 passenger capacity. And of course Type 2 doors as well after the wing. The 9 followed very soon after the 8, and that's in airline service and has been for several years. And coming soon will be the 10. This has started but is still in its certification flight test program. The lengths of the family go from about 35 to just shy of 44 meters. So the 10 is certainly by far the longest of any 737 ever produced, and passenger capacity from about 172 up to 230. Range, as you would expect, drops off with fuselage length because of the weight. Max takeoff weight from 80 on the 7 going up to an impressive 92 ton on the Max. Now all of the Max are around about 3 ton heavier than their equivalent fuselage length NG, and the reason for this basically is the LEAP engines. Now the engines are actually only 385 kilos heavier than the CFM56. So if you double that doesn't quite obviously get to 3 ton. The extra weight difference was the strengthening around that. So that the engine struts, the wings, the fuselage, and the landing gear. But all of that strengthening enabled the aircraft to reach the higher max takeoff weights that the increased thrust of the LEAP would afford. And typically all of the operating weights are up by just over 3 tons, so you certainly get the weight back. All right, on to Powerplant. The photo on the right there shows the fan blades. On the top is the Max with its 18-bladed carbon fiber fan blades. They are actually the leading edges of those are titanium for strength. Carbon's used because it's much lighter, but has got a similar weight to strength ratio. So it's almost as strong as titanium, not quite. Otherwise, they wouldn't have had to use titanium on the leading edges, but strong enough for airline operation. What you can't quite see in the photo is the diameter, and certainly when you see a Max, it's one of the things that stands out to you is how large those engines are. So the fan diameter is increased by about 8.5 inches up to 69.4 inches, and the bypass ratio has gone up accordingly from about 5 to around about 9 to 1. Max thrust for the Max at the moment is 29,317, but there's talk of this going up to 31 on the for the Max 10. That will probably be as a takeoff bump function. I don't imagine that will be a full certified. A full max rate of I don't think we'll see a 1B31 designation, but who knows? The next year or so we'll shake that out. Fuel burn on the Max very lean, 11% down on the CFM powered NGs. So that is great. Apart from environmental advantages, but range advantages as well. So the engines themselves, the top photo there shows the Max. The big giveaway, apart from the size, is those chevron trailing edges there, which is for noise. I'll show you that in a moment. But other more subtle designs, the nacelle has been redesigned and it's got a laminar flow lip. New struts and fairings to accommodate this LEAP engine and the mounting of it. New thrust reversers and revised efflux pattern. Yeah, you can just about see on the photos the markings, the two vertical lines, if you like, where the thrust reverser comes back. It's significantly further forward than it is on the NG. And revised chine size and position. The turbine's got flexible blades, and these are manufactured by a resin transfer molding process, and these are designed to actually untwist as the rotational speed of the engine increases. This, along with improved hop section materials, gives you an overall pressure ratio of 41:1. Which is significantly more than the 28:1 of the CFM 56-7, and this is probably where the potential 31k thrust is going to come from. So yeah, here's a better look at those sawtooth pattern or chevrons on the trailing edges of the fan nozzles here. These are developed by NASA, and the idea here is that they smooth the mixing of the fan and core airflows. So rather than it being a hard boundary, it's actually more streamlined flow from one to the other. That reduces the turbulence and gives a significant reduction in noise. In the flight deck, the engine instruments, they look very, very similar to the Max, but you'll see that we've got two new crew alerts, thrust and fuel flow. And in simple terms, thrust will illuminate if the actual thrust is more or less than the commanded thrust. Fuel flow will illuminate if the actual fuel flow is abnormally high compared to the FMC expected fuel flow. So that could be, for, well, say if you got the gear down or what have you. And note that the entire block will blink for 10 seconds, then remain steady amber for as long as the condition exists. All right, bowed rotor motoring. Here it is. This is one of the drawbacks of the Max over the NG. That LEAP engine, the start sequence is different, and it takes a lot longer to start than the CFM 56. It actually takes about 3 minutes per engine, particularly on a quick turnaround. First flight of the day, you can probably get one lit in about 90 seconds from cold. So not that much different, but if if you've only landed within the last hour and you go to start it up again, it'll take 3 minutes per engine, and meanwhile you've got a queue of traffic behind you at the airport. Anywho, so what happens in the engine after the engine start switch is moved up to ground? Notice I'm using the phrase start switch, not start lever, trying to relearn that phrase as the start levers have changed in shape. That actually happened on the later NGs. But anyway, the EC then starts a bowed rotor motoring sequence, and this is to straighten the N2 shaft, which might have bowed, i.e. dipped or bent, due to the difference in heat between the higher and lower parts of that rotor from the previous shutdown. Now, most of the bow occurs within the first 45 minutes of shutdown, but it can remain there for, we're told, up to 7 hours. So potentially you could have this longer start up to 7 hours after a previous flight. The bowed rotor motoring will last anywhere from 6 to 90 seconds, and this happens at between about 18 to 24% N2. The actual time in N2 will be determined by the EECs, so it will do the computations, and basically what it's looking at is the internal temperatures, and I guess ambient temperatures as well, although ambient temperatures of course have an effect on the internal temperatures. So the EEC sorts all this out, and all you have to do is sit and wait for it to happen. It's a good game between you and the FO is guessing how long it's going to be in motoring before it puts the fuel in. Yeah, I imagine that's probably all we can do to relieve the boredom at that stage while we're waiting for them to light. What also happens during the starting, so 25% N2 or max motoring, when you put the start switch to idle, the EC then performs a test of the, two tests, the thrust control malfunction accommodation, TCMA, and the electronic overspeed system. So both of those are go through a self-test process, and what you will see is that the fuel flow indicates 0 as the fuel shut-off valve opens and closes repeatedly, and the engine valve close light illuminating bright blue until the test is finished. After that, the start sequence will continue. Starter cutout on the Max is up to 63% from the previous 56% of the NG. The engine panel on the aft overhead panel is significantly different. I've shown you both here so you can compare and contrast the NGs below, the Maxes above. So you've got 3 new lights on there, or 2 new lights and a new pair of lights. So the first one is the reverser command light, and this is simply warns the crew that the reverse thrust lever is not down in flight. This is inhibited on the ground, obviously, because you will need to use reverse thrust on the ground. But should that lever rise from the stow position in flight, you'll get the reverser command light on. The next one is the reverser air ground, and this will illuminate when the air ground thrust reversal logic has failed. I mean, either of these 2 lights are not good news, because they're warning you that there's a potential for reverser selection in flight. And then finally the reverser limited light. Now there's a fault being detected on either engine 1 or 2 here, which will limit reverse thrust on the indicated engine. Now, if commanded, reverse thrust will either not deploy or be limited to idle. So if you get this, I mean, it's a lot safer than the other 2, because the other 2 are warning of a potential in-flight activation of reverse, which obviously is potentially catastrophic. Reverser limited just means you may not get reverse thrust on landing, and depending on the runway you're landing on, that may also be catastrophic. So worth doing a performance check before. If the reverser limited light should come on in flight. Okay, on to the landing gear. Starting with the nose landing gear is 8 inches longer. This, as I'm sure you all know, was to give ground clearance for those larger LEAP engines. As a result of the nose gear being longer, the nose wheel well and hence the doors had to be extended. It's a little difficult to see in this photo. I've tried to grab 2 photos of a Max and an NG side by side, so you could see it. Luckily, you've got a vertical drop down from the ground power there, so you can, if you see where the ground power is on the lower photo, you can see that door is longer, has been extended. But certainly the aircraft sits a lot higher off the ground at the front. The main landing gear has also been strengthened to enable higher weights. Now, because of that nose landing gear being 8 inches higher, what happens is the aircraft kind of pivots around the main gear axle, and that effectively it really lowers the fin height. The fin is the same. It is the same fin. It is just 4 inches lower because the nose is 8 inches higher. It's a seesaw or a pivot or whatever you want to call it. Really, I can think of no operational use for us as pilots for this. It doesn't affect your handling qualities, you know, your VMCA or VMCG. The rudder is the same. But I guess for engineers who want to get the aircraft in and out of a hangar with minimum clearance on the doors, that might be useful. All right, nose landing gear. Love this photograph. Beautiful one. Sent to me by a pilot from the States. To accommodate the longer nose gear, the forward bulkhead has been moved forward closer to the nose, because that was at the front of the wheel well. Well, it still is at the front of the wheel well, but the front of the wheel well is now closer to the nose of the aircraft. That shrunk the size of the forward equipment compartment, which you can see very nicely highlighted in black in front of the nose gear. Now, with that being shrunk, some of the kit in there had to go, and it was the weather radar controller that went, and that was moved just further back into the E&E bay. Okay, the Max 10, as you may have heard, the main landing gear had to be redesigned, and this was because of the fuselage length. So the fuselage, as we know, was lengthened 66 inches or 1.68 meters in metric. Now the gear had to be modified to enable adequate clearance of that longer body for rotation on takeoff, and also for landing to a lesser extent as well. And this was to ensure the aircraft remains stall rather than pitch limited. So how on earth do you get around this? I mean, the original plan was to lengthen the main landing gear, but if you do that, then you would have to move the main landing gear further outboard from its present position to fit into the wheel well, because the keel beam is the limiting factor here, and that the keel beam needs to be there, and presumably it's at the minimum dimensions it can be at. So what they did was the engineers came up with this great solution, which I've actually got this graphic from the patent, and it shows how you've got this semi-lever design, or trailing link as we probably know it, that shifts the rotation point slightly to the aft, and the gear is also telescopic and contracts during the retraction to fit into the existing wheel well footprint. Now, details of this were released in a video by Boeing in a couple of years ago, in August 2018, and the 737 chief product engineer Gary Hamatani actually states in it that Boeing has settled on a lever design that enables the gear to extend 9.5 inches on rotation during takeoff. Now, in addition to the lever, it's got a steel shrinking mechanism, so that there is a lever that pulls the inner cylinder up as the gear retracts, enabling it to fit into the wheel well. And perhaps most importantly for us from a pilot's perspective, there's absolutely nothing different from the Max 10 landing gear or the operation of it to the existing Max family. So let's hear from Gary Hamatani demonstrating and describing the Max 10 landing gear in person.
We wanted to preserve commonality in the Max family. We needed to get the landing gear back into the same unchanged wheel well of the Max 8 and 9. To do that, we've added 9 inches of capability to the gear lengthwise when the airplane rotates. And to do that, we put in this new lever. So this is really the key. This is on the ground, and this is when we rotate. And this lever extends down that 9.5 inches to provide us that rotation. Now what I have here behind me is a 3D printed plastic model, half scale, that represents the complete design functionality. Now to get us back into the same wheel well, the engineering team has come up with an innovative shrinking mechanism. And this mechanism, when we retract the gear, as I'll do right now, will pull up the inner cylinder and allow us to be positioned the same as the existing Max family today. From a pilot's perspective, there's absolutely nothing different between the Max 10 main landing gear and the existing Max families.
All right, so one final thing to say about the landing gear is the panel itself. It's been sort of shrunk and moved. The handle is now a shorter 2-position handle, so it's only up down. There's no off position anymore on the Max, and trying to unlearn that motor memory of not going to the off position will be fun for all. The lock override trigger that used to be beneath the lever, because the lever is now so much shorter, that's been removed and it's replaced by that lock override button just on the upper right of the lever. So how they managed to get rid of the off position? Well, if you think about what the off position did, why we had to do that, it was to depressurize the hydraulics from the actuators. Now that has now been automated through the PSEU. If you've watched my PSEU video, you'll recall in there that I mentioned that the landing gear is one of the components which goes into or feeds into the PSEU. So the PSEU has got the brains and the ability to automate functions as a result of this. So it will now automatically de-energize the hydraulics to the landing gear 10 seconds after all the gear are up and locked. All right, fuselage next. Now, one curiosity is the fuselage length has been increased by 41 inches or 112 centimeters, and that is all at the rear. It's all because of a new reshaped tail cone. So it's nothing to do with passenger capacity or anything at all like that. The distance from in front of the APU to the nose cone is the same as their equivalent, you know, the 700, 800, 900 series. What's changed is the tail cone itself. That is what has increased by 41 inches. Now, even with a 41-inch increase, the overall length of the aircraft is still the same, and that is because the aftmost point of the aircraft is not the tail cone. It's actually the trailing edge of the horizontal stabilizer. So the length of the aircraft is the same. You don't need to worry about this for turning circles or turning radii or anything. It's the same length aircraft. So this tail cone, that's what it looks like. The picture on the left is the Max, very curvy, hourglass figure. Compared to the NG and indeed all previous generations. Those curves apparently give it a 1% reduction in fuel burn. So looks good and functional as well. Again on the drag reduction front, The horizontal stabilizer straightlet, that's the bit where the stab meets the fuselage. That has been recontoured, and you will see the curve there on the upper photo where it's kind of blended in to meet the fuselage, and that dramatically reduces interference drag, which would be the two differences of airflow patterns between the horizontal stab and the fuselage at the point where they meet. So that contouring blends that out nicely. On the looking right back at the tail cone here, what you first notice is that the aft body vortex generators, which have been on since the 100 series, they were removed briefly for some very early production 300s, but quickly put back on. These have now been removed. The reshaped tail cone renders these absolutely redundant, and again there's a drag reduction benefit to not having vortex generators, as you can imagine. The APU cooling adductor has been removed, so that's the upper of the two APU holes there, the bottom one being the exhaust, the other one, the upper one's the cooling adductor, and that's now at the inlet door. I'll come on to that when I talk about the APU in a moment. And finally, visible on this picture, you can see the APU air inlet door actually closes flush to the fuselage. Again, I'll mention that in a moment. So, talking about the APU, let's have a look at it. It's still a Honeywell 131-9 brackets B, the B standing for Boeing because it's the same as the 320 family, which has got the bracket A for Airbus. But it's updated to a Series 41. Various minor improvements, as you might expect. Improved starting reliability is the big ticket item for us as crew. Power rating still the same as it was on the NG, so it's actually no more powerful an APU than the NG. It's just a better starter. The APU air inlet, as mentioned before, it's completely retractable flush closing door, giving less drag in the closed position. Now, I learned only a few weeks ago from one of you out there who put a message on my 737 Tech group, the Facebook group. Because somebody asked a question, why doesn't the APU door close fully on the NG? I didn't know the answer. I'd never even thought about it before. And apparently on the NG, it was that because there'd be a pressure differential between the outside air at the back at the exhaust and at the front, that pressure differential would cause that when the APU is not running, that pressure differential would cause the APU to start windmilling in flight, which is undesirable. So what they did on the NG was they leave the APU inlet door open slightly even when the APU is shut down. Which begs the question, why don't they do it on the Max? Because this, as you can see, that door is well and truly closed in the closed position, and there is no air getting in there. So either they now feel that windmilling is acceptable, or they've got some other means of stopping the windmilling occurring. I don't know what it is, and again, if anybody knows, put me out of my misery, let me know, and tell me why the difference. Anyhow, moving on, as this was supposed to be about the Max and not the NG. So the door's got three positions: closed, as you see in the upper photo, ground open, which is in the lower photo, and then an intermediate position, which I can't take a photograph of because it's the flight open position, which is just 17 degrees. So it's about a third of what it is on the ground open position. You can dispatch with the door locked in the ground open position, and the APU can be used in that configuration, but some buffeting may be experienced and a fuel burn penalty of 2.8% should be applied. See your MEL/DDG for the appropriate corrections to that, but that is certainly in the Master MEL, that's what they were quoting. The adductor cooling, as I mentioned earlier, remember that second upper hole on the back of the NG exhaust, or the NG tail cone, that's moved here, and you will notice that the APU air inlet is divided into two. So there's the turbine air going in the larger duct on the top, and cooling air goes in the smaller lower duct, and that is where the oil cooling and APU cooling air goes. So it's a different intake mechanism. On the panel in the flight deck, first thing you notice is that the gauge has gone. Boeing deemed it redundant. It's all taken care of by the FedEx inside the APU. We as pilots apparently don't need to know if there's if or what the EGT is. So they've taken that away from us. The blue maintenance light of the NG has been replaced by an amber door light. Now I've got a theory for this. I don't know if this is true, but I have a theory that the reason they changed this was because they have changed, and I will come on to this later in the presentation, the PSEU light on the Max is now called maint. And you can't have two captions with the same name, because I mean, how would you record it, a defect of that caption or an occurrence of that caption in TechLog? So my theory is that because the PSEU, the scope of the PSEU light on the Max was extended to other maintenance functions, one of them had to give, and it was this one. So this one is now called door. And it's amber. This will illuminate when either in flight the door's not in the in-flight position, on the ground the door's not in the ground position, or in the air on the ground if the door's open but the APU is shut down. So there you go. So this light is now purely about the door. That means that any of the other maintenance messages for the APU have to be communicated else some other way, and what they do is they appear as status messages now. So there are 3 new status messages which take the place of the old functions of the maintenance light, and these are APU generator, APU oil quantity, and APU door. Generator is just a shorter diode. There you go, engineer speak. APU oil quantity, it's low, but there's sufficient for 30 to 50 hours of operation at the maximum oil consumption rate before low oil pressure shutdown occurs. So again, just as on previous generations, if you get an APU low oil quantity, it's not the end of the world. You get, well, here 30 to 50 hours. So more than enough to get you back to a maintenance base for a top-up. And APU door. So the APU inlet door didn't reach its commanded position within 165 seconds. Now that will also bring on the door light. So it's just a kind of belt and braces for door. Alright, on to fire protection. We got this new caption now, which is equipment smoke, which lives on the equipment cooling panel just below the supply exhaust switches. There's a smoke detector in each of the equipment cooling supply and exhaust lines. So that's 2 smoke detectors, one in the supply line and one in the exhaust line. These are in the E&E bay. If smoke is detected in either the supply or exhaust lines, the following will happen. First off, that light will illuminate. Second off, the aircraft will automatically reconfigure for the smoke clearance mode. So the packs will go to high flow and the recirc fans will switch off. It does that for you. This is fantastic. This is automation at its best, I think. And finally, it will prepare for or configure for what's known as a purge mode for the supply system. So after 5 minutes, after the smoke alarm has gone, so the detection's finished, the supply fans will restart and they will purge smoke from the ducts with the detector inhibited, and that's to avoid false alarms, because you can imagine if there was smoke there and this is just trying to purge the smoke after the source of the smoke's being extinguished, so there's no more smoke being generated, but you've got this smoke in that you want to just get rid of. If you suddenly blow that around, it's going to set the smoke detector off again. So it cleverly inhibits the smoke detector while it's in this purge mode. One other thing to note is that if this equipment smoke light if the equipment smoke light will be inhibited if there is a forward cargo compartment fire alarm, and that's because our crew procedures are different from the equipment cooling smoke procedures. So rather than I guess confuse us or set us off doing the wrong thing, Boeing in their wisdom have decided the important one is the cargo compartment, and it will inhibit the equipment smoke. Right. So there we go. Significant improvement. For the wheel well, the fire detection system. Now this is the fire wire that runs around the ceiling of the wheel well, the main wheel well. It's a dual loop. It's not just a single loop. So if you look in the in your wheel well of your NG or your classic or original, if you're still flying them, you've got a single loop of this firewire, and I've highlighted it in that red oval. But this photo's from a Max, and you'll see that there are a pair of wires following pretty much the same path. So it's better wheel well fire detection. Air systems. Okay, you will see in the FCOMs references to the Integrated Air System Controllers, the ISCs, and this is what they look like. So that's in the E&E bay of a Max, and you've got two identical units there. One for the left and one for the right, each managing its respective engine bleed system and aircon system. Now these, what they do is they allow the aircraft to digitally tune the amount of bleed air that is needed, and this is a huge advance. So previously it used to be what was described as an all or nothing system. So if it was if the aircraft was taking bleed air, engine bleed air, it was taking it all. It was a binary selection. It was either on or off. But this will actually modulate and take just the amount that it needs, and that means that very often it's taking less bleed air than it would have done on an NG. And taking less bleed air means that we've got more engine performance and or better fuel burn. So it makes the aircraft run much more lean. These ISCs, they combine the air conditioning pack function, pack control functions, and the engine bleed air supply control functions into a single controller. So they are very smart. They do look at the aircon demands and regulate the bleed air by linking the two things, by merging them into one unit, as you see here. And as I say, these will digitally control the 4th and 10th stage bleed air in response to bleed system demands. The pneumatics panel is the same on all models of the MAX. Those of you who flew the short body previous generations, either the 6-700 on the NG or the 3 and 500 on the classics, will recall the panels were different. There was only a single recirc fan, and it was pack trip off instead of pack, and bleed trip off as well. So there were differences there. It's the same for all. I guess Boeing were assuming that there weren't going to be as many short body aircraft, i.e. the MAX 7s, and thought, well, for commonality, cost savings, let's just have the one system for all. So it's probably overkill on the MAX 7, but it's saved by cost savings for commonality. Okay, looking right up at the top, that rather sparse area to the right of dual bleed, that's where the ram door full open blue lights were. They've gone, because again, this is all controlled by the ISC now, so those lights are redundant. The bleed trip-off lights are replaced by bleed. And again, this is a byproduct of the ISCs, so it's able to tell you more about the system, and indeed about faults in the system. So what bleed now tells you is that a bleed is tripped off due to either excessive bleed air temperature, excessive bleed air pressure, or under pressure. Now, under pressure is a new one. Again, that's something the ISC provides. Or that there's a failure in the bleed air system, which again, by that, it probably means the ISCs, or that there's an incorrect bleed configuration after takeoff or go around. So again, it's smart enough to know that you've not configured the panel correctly, and it will alert you. Faults. You see, I've put this in parenthesis, in speech marks. Now, engineers are told that for the MAX, faults captured in the onboard maintenance function, which I'll describe toward the end of this presentation, should be relied on for troubleshooting purposes rather than observed flight deck effects, such as duct pressure needle splits or erratic movement. Now, a great example of this is the after landing duct pressure split. So after landing, I don't know if any of you flying the MAX have ever noticed this. Perhaps the FOs will, because it all happens above their heads. They might spot it. So after landing, the ISC incorporates an under pressure protection, and it conducts a post-flight bite check, called a PF bit, of the pressure shutoff valve solenoid after landing, and this causes the duct pressure to split, and it's normal for a MAX. So no fault messages will be generated because the system is operating as designed, but you as the crew will see this duct pressure split. In fact, you'll see it flapping around several times while it conducts this bite check on this component. Now, personally, I think the message this sends out to engineers is well intentioned, but what I wouldn't want to happen is for crew to stop reporting what they see as unusual or non-normal behaviour in in anything at all, but in taking this particular example in the duct pressures. And I guess what it comes down to is is knowing what is normal. You now know, because I've told you that it is normal after landing to see this duct pressure split whilst this check is being conducted. If you know that's normal, then you won't report it to the engineers. If you didn't know it was normal, then you would. And I guess where Boeing were coming from was that they were getting a lot of reports of this, probably because they didn't document that this was going to happen, which, you know, that's on Boeing. So I guess my takeaway message is know your aircraft, and if you think you see anything that is not normal, then please report it to the engineers. Oh, just one other thing to say. This photo I've used is a stock photo from I think a classic. It's not exactly. It was the only photo I had of the of a decent duct pressure split. So so that's not actually a panel from a Max, but that is a good representation of what it does. Okay, the anti-ice panel. Differences from the NGs. You've got a probe heat auto on instead of off on, standard with the Max. So those can be left in the auto position now rather than being switched to the on position, you know, and then off again, you know, on turnaround. The Max engine anti-ice panel's got a new amber caption of engine anti-ice. You'll see it down there, highlighted by my red oval. Now, when illuminated, this indicates that the engine cowl thermal anti-ice system has been inhibited due to a system failure, or when an engine core anti-ice valve fails closed. And by system failure, what they mean is, again, the AASI. This is possible because of those controllers. The engine and wing anti-ice captions are now amber instead of blue, and they've dropped the word open. They illuminate when in transit, or if the valve's in disagreement with the switch position. So if the ice is off or on, then the lights should be extinguished. So these will only come on in transit or if there's a disagreement. So very, very similar logic to the blue lights, but for whatever reason they've got rid of blue and harmonized on amber. All right, miscellaneous. Yeah, these were bits and pieces that were too small to form a chapter of their own. So let's have a look at what we've got. All right, so the ultimate VMO MMO switch. This actually is there on later NGs. It's been in for a couple of years, but not many of them. But it's in as standard on the Mac, so I'll explain it here. And in the background, you can just about see the integrated system computer on the rack, or the left one. So what this is, if you need to conduct a gear down ferry flight, then the engineers will, if you ask them, they will switch this switch to alternate, and what that does is it adjusts the VMO MMO envelope, warning envelope, to enable the overspeed warning to reflect the configuration. Again, a picture's worth 1,000 words, so what you've got is the VMO MMO normal graph there in the solid line, so 340 knot, decimal 83. But the activation points are reduced back to 270 knots and decimal 73 in alternate mode there. So a useful thing to have. Anything that stops us having an overspeed is useful in my book. Venturing into the world of trivia, the blue flight deck call light has been removed. No idea why. I'm guessing it was cost saving or weight saving or what have you. But anyway, it's gone. And yet they leave the no smoking switch in. I don't understand this at all. I mean the space at the bottom of this panel was for rain repellent on the originals and the classics, and they got rid of those because rain repellent went, and yet they keep the no smoking switch on. it defies logic. But anyway, so they've put on a brand new aircraft in up stickers over the no smoking sign. In fairness, some of them I've seen it written chime only. Anyway, there we go. Lights. This again, this was on later NGs, but for those of you that missed it, or those of you flying old NGs and about to transition to the Max, the lights panel looks like that now. So your landing and turn off lights are now all within the one unit at the wing root. FMC. So update 13 was actually designed for the Max. And it was used as 13.0 on the test fleet, and it basically brought the features of update 11 and 12 to the Max, but no new functionality for the NG. Although it did do no less than 17 bug fixes from 12 and 13. So if you're in an NG, then you would have hoped to have had update 13. As I say, it brought you nothing new in the way of features, just bug fixes. But for the Max, it needed it. So there were three main differences for the Max. The engine logic. So the TRM and takeoff speed, and the new engine performance model and thrust rating model were all updated for the LEAP engine and the Max airframes, as you would expect. The second point's kind of almost trivia. It's just data output on the Ethernet to the Max display system. The third one's probably the most interesting, or arguably the only one interesting to us as pilots, and this is a percentage D rates and variable takeoff ratings, and I've highlighted that on the lower photo there. So they're actually they're actually riding 10% and 20% D rate, which is what takeoff 1 and takeoff 2 used to be. So it allows selection of these on the M1 limits page, but based on the existing function of the fixed D rates. Now, something I'll draw your attention to on this lower photo is that M1 limit page number. It's page 1 of 13. Unfortunately, I don't have any of pages 2 to 13 to show you, but what they are is it's a list, a database of airfields and runways, and you can pre-select your airfield runway combination, and it will automatically then give you the appropriate D rate for operation from that runway, which is useful to save the company money and engine life and what have you. Rather than blasting off at 28k every time, then you can use these fixed D rates. And again, these are fixed D rates. This is not assumed temperature thrust reduction. You can do assumed temperature thrust reduction on top of the D rates. So you can really bring the engine power back, which, as I say, if you're a bean counter, that saves you money. If you're a pilot, that means that you're operating further away from the red line, so you've got less chance of having that engine failure at V1, because the engine is having to work less hard. Anyway, update 13 was superseded by 14 in May 2019. So you should all have update 14 by now. MCAS, well, as you know, I've done a couple of videos dedicated to this subject, and full details are available in those. But this is a one-page summary of MCAS differences. So both alpha sources are now used. You got split vane monitor. So if one alpha is more than 5.5 difference from the others, it rejects them. because obviously it doesn't know which one's wrong. It's got a mid-value select integrator, so that basically uses left probe, right probe, and the previous valid alpha signal to go for a mid-value of those three. And a future third synthetic angle of attack source. This is going to come in with the MAX 10. That's going to be part of the certification flight testing for the 10, and it will be retrofitted back to all other MAXs. The FCCs now cross-monitor each other, so rather than just having one FCC in use per flight in isolation, they will now cross-monitor each other. MCAS is now limited to one stab input per high alpha event, and the max commanded limit has been reduced, so it will not be able to have such a catastrophic effect as it has previously. And finally, the mechanical control column cutout functions are now replicated using the new FCC software. So this was if there was aft trim, you could stop that by moving the control column forward, and vice versa. And that function is now replaced with the FCC software. The stab trim cutout switches have changed on the MAX. Again, the wisdom of that was brought into question with those two early MAX accidents. I have to say, personally, I'm a little surprised it didn't change back. But anyway, the MCAS system was rendered safe in many other ways, so it's now probably a moot point. But you recall that all previous generations had separate stab motor cutout switches for the main electric trim switch, i.e. those on the yoke, and the autopilot trim. So these switches obviously designed to stop a stab trim runaway on a MAX, they're combined. So either switch will deactivate both the main electric trim, autopilot trim, speed trim, and MCAS stab trim inputs. So all stab trim inputs except for manual inputs. And there are only two switches there for redundancy. The functionality is the same between the primary and the backup system. And as I say, manual trim is always available, even with both switches in the cutout position. The GPS now has a runway awareness and advisory system, and hence there's a fourth switch on the row there, which is runway inhibit. The criteria for when this should be used are given in the FCOMs. I've listed the approach criterion here, just of interest. And this is really for those of you who are not flying the MAX with the RAS system yet, just for your information. Obviously, if you are flying this operationally, consult your FCOMs, but for those of you who haven't got it yet, one little sneak preview, then here it is. So the occasions in which you would inhibit the RAS system are if the airport or runway is not in the FMC nav database, and that is usually when an airport's just built a new runway and it's not in the update yet. And I've certainly had this a couple of times in my flying career where the GPWS has been screaming at me when I've been approaching a good, albeit brand new runway. The airport's not in the GPWS database. A NOTAM applies to the intended runway. Again, seek your company guidance as to what that NOTAM might be. Airline policy prohibits the use of the RW, the overrun, for an airport or runway. When you're conducting landing hold short operations, touch and goes, remember that for those of you who are base trainers. Landing altitude is above 10,000 feet pressure altitude because you can't do the calculations properly, and the OAT is out of limits, i.e. below -40 or greater than +50. And the gross weight is greater than the max landing weight. So that's an overweight landing condition there. So that's probably one to bear in mind. All right, onto the wings. The upper photo there is an arty photo of a MAX wing leading edge. A little difficult to work out at first, but the AT winglet over on the right, and that's your leading edge device at full extend there. So you've got a high gauge aluminium wing for increased strength. Increased strength because of the increased weights that the aircraft is operating at. You've got 3 more leading edge vortilons inboard of the original 3, and the lower picture shows the 3 that we've got on the NGs. The upper picture you can just about make out a row of 6 of them there, all for sound aerodynamic reasons. The vortex generator pattern has changed, but there are still 8 of them. I don't unfortunately have a decent equivalent photo of the NG from that angle to show you the before and after. But I mean, again, we're back into the world of trivia. I'm just trying to be comprehensive with the differences here. So there are the patterns change, but there are still 8 of them. The Kruger flaps, those are the ones inboard of the pylon here. They're reshaped for nacelle and thrust reverser clearance, as you would imagine. The flap limit speeds. Now these have changed very slightly. We got a max 8 placard on the upper picture and a max 9 placard on the lower picture. So for the 8, the flap limit speeds are the same as for the 800, except for the flap 40 position, which was 162 knots on the 800, and it's now 166 knots on the 8. The flap limit speeds for the 9 and I believe the 10 are increased over the 900 for flaps 25, 30, and 40. So those 3 placard speeds have been increased. AT winglets. That's the new look of the Max on the upper picture there, standing for Advanced Technology, or to give it its full name, Natural Laminar Flow Advanced Technology winglets. These are said to reduce fuel burn by up to 1.8% over blended winglets. Probably a bit less than over the split scimitar winglets, but I'm sure there will still be a decent fuel saving. Boeing's words on the AT winglet are that it further redistributes the span-wise loading, increasing the effective span of the wing. The AT winglet balances the effective span increase uniquely between the upper and lower parts, and therefore generates more lift and reduces drag. This makes the system more efficient without adding more weight. There you go. So that wingspan, it's actually increased 5 inches over blended winglets, or 1 inch over a split scimitar winglet, and the new wingspan is 35.92 meters, or 117 feet 10 inches in old money. And you can see I've done a table down there at the bottom left of the various spans. Interesting to see that the evolution from no winglets all the way through to AT. You've got a 1.5 meter distance, which is quite significant. Okay, onto the fly-by-wire spoiler system. So the whole spoiler system on the Max was changed. I mean, significantly changed. Ripped out and started again, really, to improve the production flow, reduce weight, and improve stopping distances. So it wasn't all about weight. Certainly for us as crew, it improves the stopping distances, and we like that. Okay, this hideous schematic, you will recall if you watch my flight controls roll presentation. I'm not going to build it up again for you. I just draw your attention to the bits I've circled in red. So the aileron spring cartridge, the spoiler control quadrant, the spoiler mixer and ratio changer, those 4 components, they've gone. In the Max, it's all replaced by a spoiler control electronics unit. And there's a transducer from the speed brake lever, so it's now an electrical connection from the speed brake lever rather than a mechanical one. In the wheel well, what you will see is that basically there's a lot more space. It's a lot less busy. It's still busy, I grant you, but it's less busy. You remember the huge white unit that hung on the wall there? That was the spoiler mixer ratio changer. That's gone. That had been on there since the very first Boeing 737 back in '65, and that's gone. So all of the mechanical spoiler components in the wheel well, including the aileron spring cartridge, but with the exception of the ground spoiler control module, which is the unit I've labelled up there in the top right of the picture. So that is that's the sole survivor. They've all been replaced by the spoiler control electronics unit, which is in the E&E bay. And what does that give us? The following 3 pages of features. Spoilers. So this is a new caution light, that 5th caption in that block of 5 down at the bottom right of the flight controls panel. This will indicate a spoiler fault as sensed by the spoiler control electronic unit. That means that one or more spoiler pairs are inoperative. It also gives us maneuver load alleviation, and this basically replaces the old speed brake load alleviation system. And what it does is it retracts any extended speed brakes during maneuvers that result in the high load factors that would reduce the wing root bending moment, and this allows a lighter wing box to be made, which keeps weight down. So what you're doing is you're reducing the strain on the wing, you're reducing the bending moment by this maneuver load alleviation function. If you think about it, using too much speed brake in it, like for instance a loaded turn, high G turn, would really cause the wings to bend. So what it does is says, well, I can't do anything about the G that the guy's pulling, but I will reduce the speed brakes. So it takes matters into its own hands and drops the speed brakes by as much as it needs to bring the loading back into limits. Landing attitude modifier. So this does 2 things, or is operative at 2 regimes. First of all, flaps 15 to 30. If the thrust is back near idle, it slightly raises the flight spoilers to increase drag, and that gives you a better glide slope capability. So this you don't really need this on most approaches, but if you're doing a tailwind approach, or you're on a slope of greater than 3 degrees, 3.2, certainly up to 3.5. Basically, the steep glide slopes it will be able to handle much better thanks to this. Then a flap 30 or 40, and when below VREF plus 10, the flight spoilers will raise slightly to reduce the lift, and that means that you will need a higher angle of attack and hence a higher nose attitude to give an acceptable nose gear contact margin. Now again, this is a balance, because I can see, I can hear what you're all thinking is we don't want the nose higher or higher than it needs to be on landing, because that means that the tail is going to be lower than it needs to be, and if you're flying a 9 or indeed a max 10 come the glorious day, then obviously tail strike risk is something which is at the forefront of the mind. I'm assured that Boeing have sorted all this out, and margins are not compromised. So there you go. Only time will tell. Emergency descent speed brakes. So this will give an increased flight spoiler deflection when the speed brakes are used above flight level 300 and the cabin altitude warning horn is active. So it knows you're doing an emergency descent because the cabin altitude warning horn is active and you're using speed brakes above 300. What it will do is it will give you more than flight spoiler. It gives you sort of intermediate between flight spoilers and ground spoilers, but only with the flight spoilers. But the deflection will be more up until, or should I say down until, flight level 300. Below flight level 300 you'll be going back to normal flight spoiler deflection. Above flight level 300 is where it's considered safe to give you the extra deflection. And the final thing that that the fly-by-wire spoilers give us is elevator jam landing assist. As you can see, there's a switch for this on the aft overhead panel, and this will give limited changes to the vertical flight path from the spoilers to assist the approach and landing if the normal elevator system jams. Now, even if you switch this switch on, it's only active when the flaps are 1 or greater, so you won't notice anything if you're clean. So as I say, it's only for the approach. Now, what happens is with this switch on, with this system on, and the flaps at 1 or greater, the spoilers will then rise to a preset position. A new datum will be made, and what they then do is they then extend a bit more or retract a bit as you move the control column forward and backwards for elevators. If you think about it, it couldn't do this if the spoilers were already down and flush. Yeah, it could raise them a bit more, which would help you descend a bit more, but you can't get the opposite effect. So that's why they rise to this new datum, so that they can both extend and retract as the control column is pushed or pulled to increase or indeed decrease your rate of descent. So that's what this is about. Okay, that's the end of the miscellaneous stuff. A couple more sections. We got the onboard maintenance system next. Now, I mentioned earlier the maintenance light, and my theory that this was why the maintenance light was dropped from the APU panel, and that one was renamed doors, because you can't have two maintenance lights. Well, this is the new one. This is what the PSEU light became, or indeed the PSEU and the SPSEU for those that fly with mid-exit doors. So this is the new look PSEU light, and this is the new look PSEU. That's the unit right there. So it's the PSU and the SPSUs combined all into one new PSU. Includes all of the functions of the previous two on the NG. There's no bite panel on the front of this PSU, because it's all done through the onboard maintenance pages in the flight deck. And again, just a reminder that the gear lever doesn't have an off position, because the PSEU will automatically remove hydraulic pressure from the gear 10 seconds after all the gear is up and locked. The maintenance light also does other things other than non-PSE, other than the PSEU stuff. That's why they changed its name. So in addition to all the PSEU stuff that it does and you're familiar with from the NG, it does a whole load of other things. It monitors numerous systems, and what it will do is it will indicate what are called status level faults. And this, I guess the best way of explaining this will be the old single channel and dual channel faults. So, for instance, on the air conditioning panel, PAC would illuminate on recall only for a single channel failure, or it would illuminate on its own if there was a dual channel failure. Well, it's the same thing with the maintenance light. This is effectively your single channel failures. It's not exactly that. I mean, I'm using an analogy, but these are status level faults. So if this light illuminates, the bottom line is put it in the tech log, tell an engineer, get it checked before you go. You can't go fly with the maintenance light on. hard faults, which are basically the equivalent of a dual channel failure, or some other hardware, they will usually bring on the system caption. So, for instance, the spoilers light that we saw previously, if that's full on fallen over US, then that light will illuminate. So status level light faults will only bring on the maintenance light. And this light, because it's of more minor faults, that is the logic behind why it's inhibited in flight and during engine start, so it doesn't distract you. So in flight, it's from when the thrust levers are above 53 degrees until 30 seconds after landing. That's the inhibit regime for this light. Okay, so into the OMS itself, the onboard maintenance system. I've shown a selection of pages there, showing you, just the examples of what the OMS pages are like. I mean, you as crew will never need to use these, but you may be curious when an engineer comes on a turnaround, because you've had some fault or other. This is just to give you an overview of what it is. So it monitors the aircraft system's hardware and software for faults, and health monitoring, and it will send alerts to pilot and maintenance staff via the enhanced DFDAU, Digital Flight Data Acquisition Unit. It can store over 75 flight hours of data. Not only that, it will analyze it and trend it in flight on its network file server. So it's not only monitoring, it's diagnosing, which is quite scary, but I guess that this is progress. I suppose to us as a pilot, anything which helps find or detect a fault or a failure before it happens has got to be a good thing. And I guess that's where they're going with this. Certainly I know, speaking to guys in engine health monitoring, they have successfully predicted failures of components, blades or what have you, or bearings, before they've happened. And the guys in main troll will pull an aircraft off the line and change a component because they've seen something in the engine health monitoring, and this broadens it out beyond just engine health monitoring, which is fairly established technology, and it's all of the other computerized systems, all the other LRUs, all of the other things that can be monitored and seen. It monitors, and it will analyze and trend it and flag up warnings to those that need to know. So I am actually all in favor of this technology. I think it's great to have. Another advantage of it is that the data can be viewed by engineers on the flight deck display systems or at the maintenance base, so they don't actually have to send somebody out to an engineer out to come and put the head in the E&E bay and do a bite check, or do any of the bite checks that you can access through the FMC. All of this can apparently be done remotely. I've not seen it done remotely, but that's what the literature says. So so a very powerful system. So examples of some of these data pages. The example I've used throughout here is of the PSEU, and as you can see, it's showing the positions of the gear lever, the gear itself, the doors, whether which particular doors are open. Also the proximity switch gaps and tolerance ranges. There are two pages of this. That's page 1. This is page 2. top half of this is showing you the takeoff config warning criteria for the PSCU systems 1 and 2, and the state of the LGTU, landing gear transfer unit. The bottom half of the screen is lost on me. It seems to be, to me it looks like dip pins and their settings, but I don't know. It's way beyond my knowledge. Is that stuff. The OMS pages, they can also allow the engineers to set the air-ground systems in the air, reset emergency exit latches, and extend the two-position tail skid on SFP aircraft for maintenance. On the NG, that's done by a switch on the card in the E&E bay, so it's much easier to do a lot of things with this OMS system. The data loader, and this, if you've forgotten where it is, it's just above and to the right of the jump seat on the flight deck. So as you open the flight deck door, it's immediate right. So it looks at first glance quite similar to the NG one, but there are some differences. That fuel test auto shut off guarded switches there for the left and right system. They're used by engineering to test the refueling panel. The maintenance selector is the same as those two selectors on the forward aisle stand. The ground test guarded switch, that enables an operational test of whatever LRU, line replacement unit, you select on the maintenance menus of the OMS. And there's a little power socket over there on the bottom left. So it's a combined 3-pin or 2-pin plug USB socket, and there are 2 more of those in the flight deck on the captain's and FO's sidewalls. All right, onto the max display system. So there's the money shot there. That's 6. Well, there were 6 7.5 inch DUs on the NG. They're replaced by 4 15.1 inch DUs on the Max. So that necessitated moving a lot of stuff around. The standby flight instruments and the gear lever got squished to the center, and various other controls and selectors went down in between the FMC displays. Those 4 DUs, they are known collectively as the Max Display System, which in your FCOMs is the MDS. So the center main panel is here, a shadow of its former self. The size of that was defined by the width of the ISFD, which is 4 inches, and from that everything else kind of followed, including the width and the layout of the landing gear panel. So I say you've got that smaller 2-position gear lever there. You've got the gear indication lights, placard speeds, the old mechanical flat position indicator, that's gone. That's now on the electronic displays that you can just see to the left there. The auto brake, MFD selectors, brake pressure gauge, they've all moved down. You can just see them on the bottom of this picture. The PFD, MFD transfer switches, they're on the lighting panels now in front of the control columns. And the mechanical RDMI and the yaw damper indicator, they've gone. They're consigned to the history books. So looking down to that forward electronic panel, you've got where the lower DU was on what was known as the forward aisle stand is now been renamed the forward electronic panel. And as you can see, you've got various items on there. This is a close-up of it. So you can see that there are 2 interactive display selectors. Same as the one on the data loader panel that I showed you several slides back. So what these do, they allow the pilots and engineers to interact with the multifunction displays. They've got inner and outer rotating selectors and a push button switch to scroll through, highlight and select different fields on the displays. Basically, you kind of think of these as your mouse on your computer. You blip things left and right, and then use the select button to select what you want. Onto the displays themselves. So this is the standard outboard display. This one will be on the FO side because you got the auxiliary display outboard. So there's PFD on the top, compass on the bottom, and they're actually very similar to the NG displays, just obviously laid out on a much bigger screen. The auxiliary display, this one's on the captain side because again it's on the outboard side. In this particular operator's chosen to show the aircraft type and the max takeoff and landing weights there. The map display, you select obviously map, there you go. You can see the maximum range for the terrain function there is 320 nautical miles, but notice that the overall range has been increased with the max to 640 miles, and the range selector, if you look at the range selector on there, the actual range numbers, the numerals have gone. It just gives you a plus or minus, so you increase by or decrease by blipping it clockwise or anti-clockwise. If you press the VSD button, that overlays the VSD. It just shoves your map up very slightly and drops the range down by 1. And you can see the vertical situation display shown on the bottom there. As you're coming in for the approach, the VNAV deviation will also show, and again you've got that overlay both on the VSD and on the right hand side of the screen. Plan mode, same as it ever was. Again, the 640 miles is a useful scale if you want an overview of your extremely long flights, transatlantic on this particular one. VOR mode is still there for those of you that miss it and want to use it. Pressing the engine transfer will move the engine instruments display from the left, the captain side, to the FO side on the inner DUs, on the inboard DUs. So that's all that does. It just throws the engine instruments over to him or to you. If you press the engine button, the MFD engine button, then what that will bring up is that will show you the secondary engine indications. So it'll fill in all the blanks if you want a closer look at the engine instruments. Pressing the system button, now depending on your airline customer options, you can get any of the things shown here. Hydraulics comes for free, you all get that. The brake temperature and tire pressure is probably one of the next most common ones. This particular one is only showing the brake temperature, which are all showing zeros at the moment. The tire pressures will be written inside those 6 tires, so even the nose gear tire pressures are shown with the tire pressure system, and the control surface position indicator is shown at the bottom. So again, yeah, if your airline wants to splash out, then you can have all of these displayed. The info button brings up the M1 speed reference page here, and you would use the selector knob to manually set the M1 and the V speeds. Yeah, heaven help you if you have to do that. That's definitely one to go back into the FCOMs and check how you do it. CR, which actually isn't shown on this panel, but certainly it's available. And this you will find on aircraft which are Cat 3B autoline capable, and it's cancel or recall, and you use this to well, as it says on the tin, to either cancel or recall any autoland advisory messages. I've shown one on there which is no land 3. The other one you might see is no autoland. Yeah, and always worth pressing this before you do an autoland on a Cat 3B. And finally, the intersection can show the CCTV camera as well, so you've got that information there if you need it. That's it. That's the Max covered. Before I go, I'd just like to thank the following people for the use of the photographs: Tiago Brenner, Freddie Berriton, Kev Dawes, Dottie Norcus, Johnny Penn, Ray Phillips, and Luis Tello. Thank you all for sending me the photos, and I hope everyone agrees they really do make the presentation much better. As always, if you've enjoyed the video, please give it a like, subscribe to my channel if you haven't already done so, and tell your colleagues. Thank you very much.